And so in section 2.2, we want to talk about these things called limits. And you've never seen limits before, but maybe at the end of a pre-calculus class, maybe some teacher might have taught you a little about limits. I'm not sure. Limits are this, we do limits. We do these problems involving limits, and it's these kind of questions. The limit, we write like this: the limit of a function as x approaches c, some number c. This is kind of abstract here for a second. The limit of a function as x approaches c has some answer called L. So, and we read it like that. The limit of the function as x approaches c is L. What I want to say is that L is a y value. Let me say, here's what this means. F of x gets arbitrarily close to L as x gets arbitrarily close, or I'm going to say it like this: as x approaches, I'm going to say it a little differently, as x approaches c from either side. And so this takes a little getting used to. We got a little chapter, we got a couple weeks to digest these thoughts. But that's, I don't know, that's a good sentence. There's a more mathematical, rigorous definition of what a limit is that it's rather confusing. I'm gonna skip over that for now. Maybe I'll address it later. So I'm trying to talk a little more plain language to you here. The limit of a function as x approaches c might be this number L. What it is the function is getting close to this y value. This is a y value. The function is getting close to some y value as x gets very close to some x value, called c. Or you could say it oppositely. You could say as x gets very, very close to c, the function is getting very, very close to some y value. What's funny is these limits are only kind of interesting when there's interesting, weird functions going on. Otherwise, this can get kind of boring. Like, watch this. The limit as x approaches 3 of this function, x squared. Now, when I'm in section 2.2 doing these limits, the title of section 2.2 is I want to do these limits numerically, and I also want to do them graphically. The truth is, I much prefer, maybe, it depends on the problem, but I kind of prefer to do limits what's called analytically. And let me just say, shoot, I'm sorry. But if I'm in section 2.3, then I do these limits analytically. I might be able to cover all these thoughts here quickly. Let's look at a graph. We all know what this is, maybe. It's just a function called x squared. It looks like this. It doesn't have holes or asymptotes or anything weird. It's just a nice parabola. And, you know, just let me ask you this. This is a different question. This question is, what's f of 3 if your function is x squared? What's f of 3? 9. Okay, thank you very much. By the way, let me just remind you what that question means. That question says, when x is 3, what is y? And the answer is 9. So the big point I'd like to make is that this is a different question. This is when x gets really, really close to 3, what is the function getting really, really close to? 9. You're right. The answer is still 9. which is why this is a little bit of a boring one. The answer is 9. And so you might say, what the hell's the damn difference? Well, I tried to explain the difference. The difference is sort of in the question. This says, when x is 3, when you actually get there, what is the y value you actually get to? 9. This says, when x is getting really, really close to 3, what y value are you really getting close to? 9. And in some functions, that might be they might have 2 different answers. Those are 2 different questions, but in this problem, they are the same answer. I mean, when x is 3, it does hit that point 9. We know that, and that sort of illustrates this question. But to illustrate this question, as x gets close to 3 from either side, like at 2.9, what is it? At 3.1, what is it? And as x gets closer and closer to 3, the y values are getting, the function is sort of moving in and getting closer and closer to that y value. Are you with me? So the answer to this is 9. Now, how did I just explain that? I think I sort of explained it graphically, maybe, by analyzing this graph and thinking about it. As x gets really close to 3, what's y getting really close to? 9. Let's look at a different problem. Let's look at this one. The limit of x squared minus 4 over x minus 2 as, that's a complicated function there, kind of, as x approaches 2. As x approaches 2, that's the limit. Sometimes I might, it's the limit of that function as x approaches 2. The limit of the function as x approaches 2. I'm looking for the answer, L. I'm looking for the answer. The answer is a y value. The answer is a y value. Sometimes we get a little confused, maybe this is too early, but x is moving on the x-axis, and some students, like, they'll start thinking about it and they'll say, oh, well, when x is getting close to 2, the answer's 2. Oh, wait a minute. X is getting close to 2. We're looking for the y value that the function's getting close to. So we're looking for some y value, some answer L.
So do you plug in 2 for x? No.
Well, yeah, you're right. This is a little tough for me at first. I mean, I'm trying to explain. So back to, if I try to stick with what the book is doing, let me say something. Let's try to do this numerically. See, his question, he had a good question. He said, do you plug in 2? Well, hang on a minute. Remember, when you're doing a limit, you don't really get to 2. That's the problem. The answer to a limit is f of x is approaching some y value as x is approaching that 2. But you kind of never get to that 2, maybe. So you're just getting really, really close. And so to analyze this numerically, what we do is we set up a little chart. And so I'm going to go up here. So this time I'm not looking at his graph. I mean, if you have a graphing calculator, you might be tempted to do that, but hold on. I'm going to set up a little chart, and I'm going to plug in some x's and some y, or plug in some x's. I want to plug in x's that are close to 2. Any suggestions?
1.
Well, closer than that. Yeah, that's one of the things about limits. 1 ain't very close to 2. We got to get closer than that.
2.9.
Well, right. I want 1.9. Right. I want to do 1.9. So now help me, please. Now, you do need to pick up a calculator now and help me. I want to plug in a 1.9 into this function. X is getting close to 2, so I'm going to plug in a 1.9. That's doing this problem numerically. And it is a little tedious. It takes, you got to plug in a 1.9. You got to square it. You got to subtract 4. You got to plug in a 1.9 minus 2. You got to divide that. You got to work it out. You're plugging a 1.9 into this function, and I want to know what you get. 3.9? Is that what you said? So 3.9 are you rounding that? Oh, it's exactly 3.9. Okay, thank you. Hey, can you get closer to 2 than 1.9? 1.99? Yeah. And this is kind of how your homework opens here in section 2.2. You do these, plug in a 1.99. Yeah. Help me do that, please. Take some work, I know. Take some typing. Take some effort there. Maybe you.
3.99.
What'd you say?
3.99.
3.99. Now, so if you had to guess the answer, what y value do you think we're getting close to? 4. Thank you. The answer is probably 4. To make you work a little harder, though, and to make you realize that this x is approaching 2 from both sides, you're approaching from either side, like I said, then what they suggest is you try a 2.1. So they're also going to want you to try a 2.1, and so you plug in a 2.1, and I'll try to be patient.
4.1.
4.1? I mean, are you
Probably.
serious? Well, I ain't looking for probably, but yeah, you do. It's 4.1? Maybe it is. It's 4.1. Okay, thanks. Can you get closer than that? 2.01. You're right. So here, this is sort of the chart that's set up. And the book may even be a little meaner to you than me. The book might throw in a 1.999 and a 2.0001. I mean, they may really make you work for it. But you're getting the point, maybe, right? And it is a little hard work to do these numerically. Anyway, what's this? Probably a 4.01. Okay. Well, anyway, then doing this problem numerically, I'm ready to say the answer is 4. And that's building a chart and doing the problem numerically. And it's not my favorite way to do it, as you maybe can tell. It's probably already not your favorite way to do it. It's a little tedious, it takes some work, but it's trying to drive home an idea. And to tell you the truth, there may be a place where I can't do it any other way, and I have to resort to this. I may have to resort to this method of plugging in very close numbers. Maybe there's no other way to do it. As a matter of fact, maybe you thought of early on, I should just plug in a 2, is what you might have thought of. But watch what happens, right? When you do plug in a 2, I mean, kind of like the last problem. Remember, on this problem, it was easy to just plug in the 3 and see that the answer was 9, right? So the last problem, I could just plug in the 3. This time, if I plug in the 2, I get 0 over 0, and that's undefined. Yeah, that's. I mean, I can't look at that and say 4. I mean, it doesn't look like a 4 to me.
So that's why they use a new method.
Can you type in this graph? Now, let's take a look at this same guy graphically. Can you take a look at this guy's graph for me? You know, again, graphing calculator helps, but when you type this in, you might need parentheses on your numerator, parentheses on your denominator to really get it right. Otherwise, it might be dividing wrong. So if you actually type it in and take a look at it, anybody have a picture of it? Thank you. Hang on. All right, thank you. Now, you might be looking at that, but the truth is, if you you might be looking at that. What kind of window do you have?
10 by 10.
Negative 10 to 10, negative 10 to 10. He's looking at what we call a standard window. You know, do me a favor. Go to Zoom on your calculator, and what you can do is hit Zoom Standard, which that's your standard window. Hang on, don't do that. You're already in your standard window. Okay. Go to Zoom Decimal. That's a decimalized window. And when it's a decimalized window, it plots the integers nice. It plots 1 and 2 and 1.9 and it plots the integers very nicely. And now you'll see a little different thing. I think what you'll see, because again, look, when I plugged in a 2, this is my function. x squared minus 4 over x minus 2. Please tell me what happens when you plug in a 2. It's undefined. Thank you. It's that 0 over 0. It's undefined. So when you plug in a 2, this is kind of an inaccurate picture. In that decimalized window, you'll see this. You'll see a little gap right there. It's actually a little hole right there. So this function is undefined at 2. It is. This function is undefined at 2. There's a hole right there. So again, listen to this now. So there's two different questions here. There's two different questions. Here's your function. Hey man, plug in a 2. That's what this is. What's f of 2? When x is 2, what is the y value? And the answer would be, when x is 2, what is the y value? And it's a hole. So the answer is, there ain't. When x is 2, what is the y value?
Undefined.
Undefined. There ain't one. Right. There is no y value. It's undefined. That's true. When x is 2, the y value is undefined. Maybe that's what these limits are kind of good for, because these limits are saying, well, damn it, the damn function's undefined. So maybe I should investigate what happens when x gets really, really, really close to 2.
Right.
What is the function getting really, really close to?
Right.
In other words, that helps me find out where that hole is. You hear me?
Yeah.
So that's what this question was. As x gets really, really close to 2, what does this function get really, really close to? I mean, that's what a limit question is. And the answer was, I didn't mean for this to be the answer was, what was the answer? We did it numerically. The answer was 4. Graphically, where is this hole? At 4.
Yeah.
Really not doing that hard of math, but I don't know, it's hard to explain. I'm not doing a bunch of hard math, really, but I am in this new topic that's a little hard to explain. It's the concept of getting really, really close to an x value without ever really getting there might produce an answer that's a y value that you get really, really, really close to without ever really getting there. I mean, it's a new little game. Our old function game was just, you plug in x's, you get y's. You plug in x's, you get y's. This limit game is, you get really, really close to an x. What y value do you get really, really close to? And you can investigate it numerically. You can investigate it graphically. I tell you what, you're gonna, I mean, and those are a little tricky. Maybe I really like doing it analytically. You ready? Watch this.
Right.
Watch this. Forget this for a second. Here's this problem. Same problem. It's the same problem. I just want to show you how I really prefer to do this. So I prefer not to make a chart and do it numerically if I don't have to. I prefer not to bother typing in the graph if I don't have to. It helps you see things though at first, so that's why we do this at first. But to really do a limit problem, I'm just going to spill the beans here. So now I'm sort of just jumped to 2, 3. Although I'm kind of going to back up. I'm in 2, 2, and 2, 3. So here you go. Step 1 of doing a limit problem. X is getting really close to 2. Well, I'll tell you what. Just go ahead and plug in a 2 and see if you can get an answer. Technically, you're not plugging in a 2. Technically, you're plugging in a 1.9999999, but god dang it, might as well just plug in a 2. Okay, so you plug in a 2 and see what you get. Well, we've already sort of done that. When you do plug in a 2 and see what you get, you had 0 over 0. Well, that's undefined. That makes you think that you're stuck maybe or something, but you're not stuck. When you get this undefined answer like this, what you can do some work. When we do things analytically, that means do some algebra, do some work. You've probably been begging to do this. So do something. And in this problem, what have you been dying to do here? Factor it. Yeah, if you factor that numerator here, x plus 2, x minus 2, right, you guys? That's the difference of two squares. It's very famous. The denominator is an x minus 2. After you factor it like that, then you can see that you can cancel this x minus 2. And maybe you can realize that that x minus 2, that's the thing that's been giving you the 0 over 0. That's the thing that's been giving you that's the issue that you've had. Once you cancel it away, you're left with this problem. What's the limit as x approaches 2 of this? And again, once you kind of do some algebra and do some fixing, you do something to fix it, is maybe what I want to say here. And once you do those steps, now you plug the 2 in again, even though maybe you're plugging in a 1.9999999, but you plug in the 2, and what do you get? 4. That's kind of how you do limits when you can. When it's a setup like that. This was set up to be fixable. He was a very fixable problem because you could factor them and cancel it and get your answer. And that's doing it analytically. Your homework, if you look at the homework in 2.2, you might see some problems kind of like that, but you're not supposed to do it like that. I mean, doing it analytically is sort of up in 2.3. In 2.2, they got some charts set up for you. They want you to do charts. They want you to look at graphs. So this is good. Again, let's do this. So now I'm just going to give you a graph. So I'm not even going to give you an equation. I'm going to give you a function. Here's a picture of some crazy function. Making a beautiful picture of a crazy function. Sorry. Look at that. It's a crazy function, man. Crazy function called f of x. And so I got some questions for you. I'm sorry, I know it's a little hard for you to replicate that, but take your time maybe. You can kind of draw that. I labeled these important x values here, and I labeled a few y values there. And I want this question. What's the limit of this function as x approaches -3? That's one question. What's the limit of this function as x approaches 1? Here's another question. What's the limit of this function as x approaches, this is how you read these things, 4? So I got 3 questions here based on this picture. So I guess you really are doing this problem graphically. It's the only way you can do it. You're not going to make a chart and do it numerically. You don't have an equation to plug things in. You're not going to do it analytically. You don't have an equation to do it anyway. You got this picture. You got a graph. So you're going to do this problem graphically. So you're going to look. When x approaches -3, what is the limit? Keep in mind, here, this is a drive this home. I love to drive this home. The answer to all these, the answer to all limits is a y value. It's a function, it's a y value, it's a function value. So as x goes to -3, yeah, I'm not trying to be tricky. I would call it 2. Yeah. Now there's a hole there, I mean, here's a different question. Okay, hold on. Here's a different question. What's f of negative 3? So what is f of negative 3? Well, there's a hole there. There is no damn y value. Excuse my language. There is no y value. So it's undefined. So when x is 3, there ain't no y value. It's undefined. That's true. But that's not what this says. This says when x gets really close to negative 3, what does y get really close to, please? I don't know what accent that was, but as x gets really close to negative 3 from both sides, I think the answer is 2. It's pretty obvious, right? It's easy in a way. It's 2. The y value, it gets close to. And the fact that it never gets there is okay. The fact that it never really gets there is okay in a limit question. Because it's not about getting there, it's about getting close, really close. Cool. What about this one? As x approaches 1, and let me just throw a little kink in there. Hang on, let's jump up here first. What would be f of 1? When x actually is at 1, what actually is the y value? Can you read my graph and tell?
1.
Good. When x is 1, there's a y value colored in right there. That is the y value. It is 1.
It's not a hole, so.
Well, right. It's a hole with a...
Yeah.
It's part hole and part filled in, right? But that question says when x is 1, is it defined someplace? It is defined. It's colored in and defined at that y value 1. Now, but when you're on the function approaching 1, you're not up there. When you're on the function approaching 1 from either side, you're just getting really close to 1. And when you're getting really close to 1, you're still on the function and you're down here and you're close to this y value, which is negative 2. I'm explaining it. It's new and different. And then this one's a little new and different right off the bat here. As x approaches 4, well, let me ask you this quick. What is f of 4? And again, that means
1.
Good. When x is 4, what is the y value? When x is 4, you see it colored in right there? I guess that's 1. Yes. So, but when x gets really close to 4, as x gets really close to 4 on this graph, see, if I'm on the graph, x is getting close to 4. Sometimes you think of x getting close to 4 like this. But you got to pretend you're on the graph approaching your y value. So your x is getting close to 4 kind of like this, on the graph. Damn.
So is it 1 and 5?
So it's 1 and 5. It's those two y values, right? Well, listen. Here's one main big thing about limits. You can only have one answer. So if you're trying to do a limit where you suspect there's two answers or you're getting two answers, the answer is does not exist. The limit does not exist. You can't have two answers. And it is a two-sided limit. I mean, when the directions earlier on said we are approaching from either side. We can't ignore one side and just do one side. So we're approaching from both sides, and because those sides didn't connect, didn't line up, I had two different answers. And when you get two different answers, the official answer to the limit is does not exist. It's not undefined, it's does not exist, which is a little bit of semantics, but.
So the one with the 1 and the 4 doesn't exist. The limit.
So the limit as x approaches 4 does not exist. What's the reason it does not exist? Because you see a hole? No. What's the reason it does not exist?
Because when you approach to the left, it's 1, but when you approach to
Because
the right,
there's sort of two answers.
Yeah.
If there's two answers, there ain't an answer. The limits should have one answer. Now, I'll get ahead of myself if I say this, but I'm just going to say this. There is such a thing as a one-sided limit,
Right.
but I haven't, that's coming up. I mean, there's almost no reason to start that now, but I'm just gonna say it.
Yeah, do it.
This is a, you know, all these limits are what's called two-sided limits, but somebody could ask you, as you approach 4 from the left, that would be a one-sided limit.
Right.
And if you're approaching 4 from the left, I think it has an answer. I think
1.
it's 1.
Yes.
They could also say, what's the limit as x approaches 4 from the right? If you're approaching from the right, and they say those words, then that's a one-sided limit. And from the right, it does approach a y value. I know it doesn't get there, but we know it doesn't matter in limits. It approaches a y value of 5.
Okay.
So from the right, it does have an answer called 5. From the left, it has an answer called 1. But this is the good old two-sided limit, and because those other two are different, it does not exist.
Right.
Did you want to?
No, that's what I was gonna say.
Okay. Let's do one more here. We're getting close to the end, but let's just do one more. I think this shows up in one of your first problems in 2.2. The limit of sine x over x as x approaches 0. You know, again, I'm struggling a little because I'm trying to teach you like the book. We should do this numerically or graphically or analytically. Now hang on, let's just forget the damn book for a second. In real life, when you're doing these limits, I think you try to do them analytically. You try to, so forget this for a minute. You try to do it analytically like I did this limit. For the most part. So watch what happens. So that means, what that kind of means is, if you remember what I said, go ahead and plug in your answer and see what you get. I'm sorry. As x approaches 0, go ahead and plug in a 0 and see what you get. You might get an answer. See, I'm sort of thinking about this. My very first problem today had no issues. My very first problem today was this one. And I don't know if you remember, but if you plug in a 3, you get 9, and that's the answer. Okay? But you know, it also turns out that f of 3 is also 9, right? I mean, these both have the same answer. If you remember what I said, they're different questions. The question here is, when x is 3, what is the y value? 9. The question here is, when x gets really, really close to 3, what's y getting really, really close to? Turns out it's 9. And plugging it in just gives you the answer. So for most limit problems, when you first see them, I think step 1 is try to plug it in. Maybe you get an answer. But if you plug in a 0, you get the sine of 0 over 0. And the sine of 0 is 0. Your calculator could help you with that. But that's a 0 over 0. And 0 over 0 is undefined. But that's what this was. See, this guy was undefined. And so when it's undefined, don't stop. Students are tempted to say, oh, okay, it doesn't exist. No. It does not exist was sort of a special thing here. These undefined things, if you get this undefined thing, it just means you need some more work. You got to do something. And so analytically, we did some factoring and we did some cleaning, and this worked well. Back to this guy. There's really no algebra to do here, is there? I mean, so here I am with this 0 over 0. I think I need to do something, but there's no factoring. There's nothing I can really do. So guess what I'm going to do? I'm going to resort to, so I tried to do it analytically. I got nowhere. Now I'm going to go do this. I'm going to do it numerically. Maybe you would think, screw that, I hate that numeric. Maybe you would try to do it graphically. And then you type in this graph into your calculator, and you get a pretty weird picture if you did that. And I don't think it's I think it's kind of a misleading picture. So I'm going to do it numerically. What does that mean? It means set up a little chart, and what ultimately you're trying to plug in a 0, but you can't plug in a 0, so you approach it from either side. What should I plug in that's close to 0? A 0.1? Is that 0.1? Is that okay? Plug in a 0.1. Or if I'm working on the other side, plug in a negative 0.1. Are you guys okay? So I'm doing it. I've decided I had to do it numerically. That's what I decided. I couldn't get anywhere. So now I'm picking up my calculator. I want to be in radian mode, and I want to ask my calculator, what's the sine of 0.1 divided by 0.1? What does your calculator say? I'm plugging in a 0.1.
0.99.
Does it really? What if you plug in a negative 0.1? The sine of negative 0.1 over negative 0.1. Does it really? Are you serious? It's really that? I mean, I know what the answer is. I just didn't think this was going to be so close, right? I mean, I thought maybe I need to get closer. See, maybe after trying 0.1, maybe I should try 0.01, right? Would that be closer? Maybe I should try 0.001. Are you following me? But wait a minute. Do you think you really need to? I don't either. I mean, with these numbers here, what do you think this answer is? Yeah. It is, and we just did it numerically. And if you didn't trust that, I mean, maybe you don't trust that 0.99. I mean, you can get closer, right? You can do a 0.000001 if you want to. Let's see what it is. So we're done with this problem. The answer is 1. There was no way to do it analytically. I had to do it numerically. All right. I'm going to quit. Thank you for listening. I'll see you Monday morning at 8 o'clock. I know you're working on your review sheet, but if you can get on into some homework in 2.2 or 2.3, that would be nice. Monday I'll open up the book and start looking at some homework problems in 2.2 and 2.3. And help you do some homework.